Hi, welcome to this MAPTCHING process to be part of the Problem Solving Expert Program, or PSE. My name is Manuel Liñán and I'll be facilitating today's session. I am the General Manager of SAC Consulting Company. Well, let's start. The objective of the Problem Solving Expert Program is to provide with the knowledge and develop the skills necessary for the participants to make sure that they will be able to solve any type of problem. In order to do that, a systematic approach will be provided through a methodology named COSMICS, invented by Manuel Liñán and that has been optimized during almost 20 years of application in all type of industrial and service companies in tens of countries around the world. In characterized phase, leadership problems, common sense problems, and measurement problems are being solved. Therefore, change management and metrology principles and tools are provided. In organized phase, all operative discipline problems are fixed. Then, quality controls and process controls principles and tools are provided. In simplified phase, problems related to capacity, volume of throughput, speed, time, and optimization of resources are solved. That's why lean manufacturing, just-in-time, and theory of constraints, principles, and tools are provided. In model phase, the problems related to high variability, poor process capability, quality or defects, scrap, rework, etc. are reduced. To be able to do that, Six Sigma principles and tools are provided. In import phase, technology, design, and adaptation of best practices issues are overcome. Therefore, theory of inventive problem solving, or TRIZ, principles and tools are provided. In correct phase, project management problems are prevented. Therefore, some principles and tools included in Agile Scrum are provided. Finally, in sustained phase, perdurability problems are prevented, and that's why some quality management principles and tools are provided. The PSC training program is very intensive, and it's made by 200 hours of in-classroom training, distributed in 6 weeks of training plus a graduation process week. Keep in mind that you have to be full-time in class during 1 week per month, along 7 consecutive months, and very likely you will have to travel to take the training outside your city. In addition, you have to spend at least 35% of work time after classes to study, because there will be written exams during each training week. And also you have to apply the new knowledge during a project that shall solve a real problem of your site. If you think that your current work and/or personal situation won't allow you to enjoy and perform the task required by the program in an effective way, please bring your concerns to your plant manager and/or to any of the organizers of the program. This time I'll be talking about modeling. We want to create mathematical equations in order to simulate the expected performance as a function of different factors. Therefore, what we have to do is to create those mathematical equations. Today I'll be talking about a simple method to create a linear model. Well, let's use this example to do this. For instance, here I'm having the relative progress of projects. We want all projects to be on time, 100% relative progress of projects. But as we can see, there is variation, or there is variability in the relative progress of projects. The hypothesis is that the relative progress of project is being affected by two outputs or two inputs. It's being affected by time spent per week and is being affected by weekly review of the manager, if the manager is reviewing or not the progress of the project. Then the equation that I think can be defined, the relationship between the variables can be something like this one. The progress of the project, P, expected, is equal to a constant plus the effect of the review of the project manager plus the effect of the time spent per week. Let's do first time spent per week plus a second coefficient of the review of the manager plus I think there can be an interaction between time times review plus minus an error. Later I'll be talking about what is the meaning of an interaction. Well, in order to build that equation, first I want to put together all the data or sort the data, organize the data in this form. Then the factors, the potential factors that I think are time, that is one of the factors, which can be low or can be high. The review of the project, which can be low or can be high as well. So we are having all these combinations. And also we are having the relative progress of projects. So this is the progress of projects. Let me talk about progress of project 1 and progress of project 2. Why 2? Because we are having 2 for each of them in this example. For instance, the first one, high hours and yes. Well, what is that? Is that a high or is that a low? Well, let's code the values. For instance, for high time, I will assign a +1. And for low time, I will assign a -1. High time +1, low time -1, high time +1, high time +1, low time -1, and low time -1. In this case, it's a little bit subjective what is high or what is low. We can think about the average of those values. The minimum is 1, the maximum is 8, so the average is about 4.5 and +1, 5.5. So basically what I'm stating is if greater than 5 hours, greater than 4.5 is high, smaller than 4.5, which is low amount of time. For review of the manager, if yes, there was a weekly review, I will assign a +1, or if no, there was not a weekly review from the manager, I will assign a -1. So that is -1, +1, -1, +1, +1, and -1. Now we can match these values with this table that I want to fill. For instance, the first value is high time. Yes, there was a review, ++. For ++, the progress of the project was 100. Second one, low time, no review, -1, -1. The average was 20%. For third one, +1, -1, +1, -1, that average is 40%. 40%. -1, +1, 60%. -1, +1, 60%. Next, +1, -1, 30%. +1, -1, 30%. That's why I have assigned 2 values for P, because I'm having 2 values on the same condition. +1, +1, 95%. So we are having 95%. -1, +1, -1, +1, 70%. And -1, -1, 10%. With that, I can calculate the average of the outputs, the average of the response, the average relative progress of project. The average is 15, 35,
65, and 97.5%. Okay, then we are having already our data. We have put together all our data. Keep in mind that this model is predicting the average relative progress of project. That's why I want to use the averages, but this is average expected. Okay, so the first thing, in order to get this equation, if I develop this equation, as I said, I will be able to simulate with that equation and predict what is the expected relative progress of project as a function of how much time the project leader is spending to her project, and if there was a project review or not from the manager of the area or the plant manager. Well, the first value that we want to calculate is the coefficient B0. The coefficient B0 is nothing else but the grand average. So B0 is equal to the average of the averages of relative progress of projects. In this example, basically, we are having 15 plus 35 plus 65 plus 97.5, and that is divided by 4. Okay, let's do the calculations. Well, the grand average, the average of the averages, is 53.125%. Then we can create the first part of the equation. The first part of the equation is the expected progress of the project, the expected average progress of the project is 53.125. This can be our equation to predict the average relative progress of project. But certainly this equation is going to have a very big error, because as we can see, the specific values are not 53.1. We are having values up to 100%, and they can be as low as 10%. Therefore, we are not predicting the variability, because that variability is being affected or being created by other inputs or factors. One of the inputs that we are having here that can be affecting to the output is the time. Then, therefore, I want to calculate the coefficient of time. This is the slope. How much the average relative progress of project is being affected when we change 1 unit to time. Well, in order to calculate that coefficient, what we can do is this. We will be calculating the coefficient B1. Coefficient B1 is the effect on the response, by the factor time. Effect of the response by time divided by 2. Okay, what is the effect? The effect on the response because of time is the average progress of projects when time is high minus the average progress of project when time is low. So we want to calculate the effect on the response on relative progress of projects when we are changing from low time to high time. Okay, let's do those calculations. The effect of time is equal to, when time is high, what is the average progress of project? Here we are having low time, we are not using that value yet, and here we are having high time. When time is high, the progress of project is 35%. This is low time and this is high time. When time is high, the average is 97.5%. And this is average, the average of the averages. This is divided by 2. So we are having the effect on the response, relative progress of projects, when time is high, minus when time is low. If time is low, which is the first value, the progress is 15. Plus, when time is low, the progress is 65%. So that is divided by 2 because it's average and average. Well, let's do the calculations. Okay, well, here we are. This means that the relative progress of project average is 66.25% when time is high. And relative progress of project is 40% when time is low. That means that the effect on the response when we are changing from low time to high time is 26.25%. In other words, the progress of the projects is higher by 26.25% when there is a high dedication of time by the project leader per week compared to when there is a low dedication of time by the project leader. Then, with this value, we can calculate the coefficient. As I have just said, this coefficient is the effect of time, 26.25%, divided by 2. Therefore, the coefficient is 13.125%. The question is, why we are doing this division by 2? Why we are dividing by 2? Well, the reason is because of this. The coefficient, as I have said, is the slope, and that means that how much the output changes when we are changing 1 unit on the output. This effect is the effect when we are changing 2 units to the input. Why is that? We have calculated the effect when we have changed from -1 to +1. This distance is equal to 2 units. From -1 to 0 is 1 unit, from 0 to +1 is another unit. Then, this is the effect on the response when we are changing 2 units, but we don't want the effect when we change 2 units. The coefficient is the effect when we change 1 unit, which is the slope. That's why we are doing this calculation dividing by 2. Well, then we are having the coefficient, and we can add this coefficient to the equation that we are building. The equation that we are building then is plus the coefficient 13.125 times time, dedication of time. If we add this term, the error will be reduced because now we are introducing variability to the output as a function of the variability on the input. But still, it's very likely that the error still be high. Not that high as before, but still high. Then we can keep adding some more predictors. If we keep adding more significant predictors or significant terms to our equation, the error will be smaller and smaller. Well, let's do the same thing for the second one. The second one, which is the effect or the coefficient for the weekly review of the manager. The mechanics is exactly the same. What we have to do is we want to calculate the coefficient B2, which is the effect of the project review by the manager per week divided by 2, where the effect of the review is the average of the relative progress of projects when there is a weekly review, when the review is yes, minus the relative progress of projects average when the review is no, -1. Exactly the same mechanics than before. Then the effect of the review is when the review is +1, what is the average on the response? When the review is +1, the average of the response is 65. Plus, when the review is high, the average is 97.5%. Divided by 2. Minus when the review is low, when the review is minus 1. When the review is minus 1, the average is 15. Plus, when the review is minus 1, the average is 35. And that is divided by 2. Well, let's do the calculations. Well, the results that we are getting are this. When there is a weekly review from the manager, the relative progress of project is 81.25%. And when there is not a review from the manager, a weekly review from the manager, the average progress of the project is 25%. Therefore, the effect is 56%. When there is a project review, the progress of the projects is 56.25% bigger than when there is not a project review. As we can see, the effect is much bigger of the project review is much bigger than dedication of time. Of course, dedicating more time to your project makes that the project has a better progress. But the effect is even bigger if there is attention from the manager compared to when there is not attention from the manager. Well, let's calculate the coefficient. As I have said, the coefficient B2 is given by the effect of the review, 56.25%, divided by 2. That is equal to 28.125. And this value should be added to the equation that we are building. The equation that we are building is plus 28.125 times review from the manager, review of the manager to the progress of the project. Well, with this, by the way, we can compare, we can do a graphical analysis. What we can do is that we can compare the effect of both doing a main effects plot. Let's do the main effects plot. Now let's do a main effects plot, which is a graphical representation of the effect of each of the factors. Here we are having the first factor, which is time dedicated by the project leader per week to progress her project. This is the input, which the time can be low or the time can be high. And also we are having the progress of the project. As we can see here, when the dedication of time was high, the average progress of project was 66.25%. Then, when the dedication of time was high, the average progress of project was 66.25%. So that is somewhere, let's say here, and that is 66.25%. When the dedication of time was low, the progress of the project was 40. When dedication of time was low, the average progress of project was 40. Then the effect is this big. The effect is this big. This distance between this and this value, that is the effect. The effect is 26.25%. So the delta here, which is the difference, is 26.25%. Let's do the same thing for the second input. The second input is manager review. For the manager review, we want to see same thing, the effect when there is not manager review and when there is a manager review on the progress of the project. So, same thing. when there is not a review, when there is a review of the manager, when is +1, the effect or the response is 81.25%. When there is a review of manager is 81.25%. Is somewhere, let's say here, and here is 81.25%. When there is not review from the manager, the progress average is 25%. When there is not, is 25%, which is here, 25. Then this is the effect of the manager review. That is the effect of the manager review. The delta, which is the difference between no manager review and yes manager review, is 56.25%, and that is the effect. The effect is 56.25. As you can see in a graphical way, you can observe that the slope here is smaller than here. The slope is bigger here than here, which means that the effect is greater on the progress of the project when there is a manager review compared to the effect of time when there is high dedication or time or low dedication of time on the progress of the project. Well, that is the main effects. Now, we want to determine the next term, which is the interaction. Let me talk about the interaction. Let's talk about how to calculate the interaction. The interaction is a an effect of a combination of levels or values on the inputs. For instance, just to give an example, if I increase the temperature, the effect is small. If I increase the pressure, the effect is small. But if I increase the temperature and pressure both, the effect can be very high. If that happens, then we are stating that we are having an interaction. The interaction happens when the effect of one factor depends on where the other factor is, where are the values or the inputs of another factor. Well, that is difficult to explain, but perhaps later when we observe to the interaction plot, we will be able to understand a little bit better what is an interaction. For now, let's calculate the interaction for this equation. For this equation, we need to calculate again the coefficient of the interaction. The interaction representation is through a multiplication of factors. In this case, I am multiplying the factor the factor time spent by the project leader times the review of the manager. So, let's calculate this coefficient. In order to calculate that coefficient, we are going to do very similar process. The mechanics is going to be very similar to the mechanic that we have done previously, which is the coefficient B3 is the effect of the interaction time times review of the manager divided by 2, where the effect of the interaction time review is equal to the average on the relative progress of project when the interaction is high minus the relative progress of project average when the interaction is low. What means that? High and low. Well, let's see here, let's code the interaction. So, we want to calculate time times review. And time times review is -1 times -1, that is +1. +1 minus 1 is -1. -1 times +1 is -1, and +1 times +1 is +1. Okay, let's do the calculations there. But using this new coding. Then the effect on the interaction time times review is equal to the average when the interaction is +1. Here, the interaction is +1. The response is 15. Plus, when the interaction is high, the response is 97.5 divided by 2. Minus the average when the interaction is -1. When the interaction is -1, we are having 35, and when the interaction is -1, we are having 65. That is divided by 2 because that is also an average. Well, let's do the calculations. And here we have the effect of the interaction. The effect of the interaction is 6.25%, which is much lower than the main effect of time, which was more than 20%, and than the main effect of project review, which was more than 50%. So this effect is smaller for this example, for this case. Let's calculate the coefficient. As I have said, the coefficient is B3 equal to the effect 6.25 divided by 2. In this case, 3.125. Then we can add that term to our equation. And then we can say that these terms plus 3.125 times time spent by the project leader per week times if there was a review from the manager per week or not. Now, the question, how do I make the interpretation to this effect? How do I make interpretations to this effect of the interaction? It's difficult to explain, or it's difficult to understand just taking a look to the number. The number itself doesn't say much to me. Then, in order to understand what is the meaning of that, the best approach is to do a graph, and we are calling to that graph the interaction plot. Let's talk about the interaction plot. Well, the interaction plot contains 3 variables. In this case, we are having our output, our response, which is progress of the project, relative progress of project, and the 2 inputs or the 2 factors, which is time, can be low and can be high, and manager review. +1, yes, there was a weekly review, and -1, no, there was not a weekly review. All 3 variables will be in this plot, in this 2-dimensional plot. So let's start. The first thing is, when there is a manager review, I will be using this blue color. This blue color is when there was a manager review. So in our data, when we had a manager review, these were the relative progress of project. So for instance, when there was a manager review, yes, +1, and time was -1, +1 and time was -1, the average was 65%. So when this was +1 and time -1, 65%. So it's somewhere around, let's see, 65%. Now, yes, there was a manager review, and there was a high dedication of time. High dedication of time, manager review. Average 97.5%. So when there was a manager review and time was high, +1, 97.5%. So it's somewhere here, 97.5%. So here we are having the effect of the manager review. The effect of the manager review. Now, let's take a look to the effect when there was not a manager review. This is the effect of manager, when there was manager review, the effect of time on the response. Now, I will be using when there was not a manager review, red. When there was not a manager review and dedication of time was low, low dedication, no manager review. The average was 15%. Somewhere here, this is about 15%. No manager review and high dedication of time, the average was 35%. So it's somewhere here. Let's take a look to the delta or the difference to each of them. For instance, here the difference is 20 units. And here the difference, the delta, is 32.5%. So that means that the effect of time is 20% when there is not a manager review, and the effect is 65% when there is a manager review. So the effect of time is greater, is bigger when there is a manager review. The effect of time is smaller when there is not a manager review. Then the factor time sometimes have a bigger effect and sometimes it has a smaller effect. It depends if there is a manager review or not. That's why we state that we have an interaction. Well, we are almost done because we are having all the coefficients for our equation. But I want to know the error, which is the error of our model. In order to calculate the error of the model, I want to calculate all the variability that we cannot predict from the factors that we are obtaining. So, if we want 95% of confidence level, that is approximately 1.96 standard deviation, plus minus 1.96 standard deviation. Then we can state that the error is equal to 1.96 standard deviations, which is the total variability that we cannot predict with the terms that we have included into our model. Well, this standard deviation is calculated by this formula that is given for the standard error, For this formula, for the standard error, we can see these differences. These differences is given by the variability that we observe here. This variation that we observe here is because of other factors that we have not included into our model. We are observing an average of 15, but if we see to the individual values, we will see 20 and 10. Then the real values are not 15. We have an error here of plus minus 5, just to say somehow. Then why are we having this variability? Because of all the other factors that are not included in our model, and those will be part of the error of the equation. Well, then the difference is basically, is this variability that we are observing here. This variation is 10 units, this variation is 10 units, this variation is 10 units, and this variation is 5 units. But we don't want the difference, we want the difference square. Well, the difference square is square of 10, 100, 100, 125. And we want the sum of all those values, and the sum of those values is 325. Okay, then we are ready to calculate the standard error or the standard deviation of the error. Well, the standard error is given by the sum of the differences squared, 325, divided by 2 times how many of these are replicated. We are having 1, 2, 3, 4 combinations. and all 4 combinations are having a replicate. For instance, if we were not having a number here, we are having only one value, we would have 3 replicated. But in this case, all of them are replicated. So G is number of replicated combinations. In this case is 4. Divided by total number of values. The total number of values are 1, 2, 3, 4, 5, 6, 7, 8. All the individual values, 8. And all of that, the square root. That is 325 divided by 8 divided by 8 and square root. If we divide this by 1, this will go with this will go with this, then is 325 divided by 64. Square root. And, well, let's do the calculations. The standard error, which is the variability that is not explained by the factors that we are observing, is 2.25. Then the error is 1.96 times 2.25, and that value is equal to the total variability that we are observing and is not part of our equation of the predictors that we have added into our model is 4.41 units. That means that this equation should be plus minus 4.41. And this will be the equation that we can use to predict our model. Well, at this point we have seen how to develop a transfer function or a mathematical equation to predict the expected performance of an output when we are having some inputs. In the example that we have done, we have developed the transfer function that we can use to predict the expected relative progress of project average as a function of time spent per week by project leaders and weekly review of the manager. To test this equation, we can do a simulation, which is at the end what we want to do because we want to be predictive. Let's use this example to do a simulation. If the time spent per week is 2.5 hours of the project leader and there is a weekly review of manager, which is the expected relative progress of project? Well, the expected relative progress of project is P expected. The time spent per week will be T in our mathematical equation, and the review of the manager is the R. Then we can use this equation to calculate the expected relative progress of project. Therefore, T actually is 2.5 hours per week, but T, which is the time, is in uncoded units. But the equation that we have built is an equation done for coded units. Therefore, we have to code this input into coded units. In our case, T in coded units will be -1. -1 because we have stated that if the time is smaller than 4, it will be -1. And if time is greater than 4, it will be +1. Since 2.5 is smaller than 4, then we are having T -1. By the other hand, the relative, well, the review of the manager in uncoded units, that is, yes, there is a weekly review of the manager. But again, since the transfer function or the equation was built for coded units, then R in coded units, it will be +1. With these inputs and this equation, then we can calculate the expected relative progress of projects. Let's do that. Let's calculate. Then, expected progress of project average is equal to 53.125 plus 13.125 times T. T is -1. We are substituting T for the number that we are using as an input, plus 28.125 times R. R is plus 1. Plus 3.125 times T times R times T minus 1 times R plus 1. Well, let's do the calculations. Okay, as you can see, the expected performance, the expected relative progress of project is 65%. Now, how can we validate, how can we confirm that we are not that far from the reality? We can take a look to the original data, and in our original data, you will observe that when T is minus 1 and R is plus 1, when T is minus 1 and R is plus 1, the expected performance is 65%, which is exactly what we have calculated from our equation. Then, in that way, we can observe that we can predict quite well the average performance, because as I have said, this is the expected average performance. Now, keep in mind that we are having an error which is plus minus 4.4. So in reality, our equation is 65 plus minus 4.41%. That would be the expected performance. There is a range, a confidence level. You can see in our original data that 65% is around plus minus 5%, which is between 60 and 70, which is close to this original data. And basically that's it. Now you are ready to do an exercise for your test. I will be providing some data to you, and it is expected that you create all what we have done. We have defined first what is the main effects, what is the interaction, the main effects plot, the interaction plots, the equation, including the standard error, and finally a simulation. Now is on your side to do this exercise. Good luck.